want you to picture something for a second. Imagine a high-tech drone flying right through the teeth of a massive blizzard.
Oh, that sounds like a nightmare for any battery.
Right. I mean, the temperature is hovering at negative 40 degrees Celsius. The wind is just howling, throwing snow so thick you can't even see your own hand in front of your face.
At a negative 40, standard electronics are basically just paperweights.
Exactly. But this drone has no GPS signal. It's dodging unpredictable obstacles like erratic tree branches and sudden downdrafts, and it is flying completely autonomously.
Which is wild to even think about.
It really is. So ask yourself, how do we know with absolute mathematical certainty that this machine won't just freeze up, glitch out, and fall out of the sky like a stone?
It's a terrifying scenario, right?
Yeah.
Especially if you view it through the lens of, everyday consumer electronics.
Oh, for sure. Like, my phone dies if it's just a bit chilly outside.
Yeah. Take a high-end smartphone out in those conditions, and the voltage drops, the battery protection circuit trips, and it shuts down in 5 minutes flat.
Yep. Just completely dead.
But a drone flying a critical mission under these conditions, it operates on an entirely different paradigm. It doesn't have the luxury of a safe shutdown.
And the reality, the engineering required to guarantee it won't fail is exactly what we are unpacking today.
We've got a lot to get through, too.
We really do. We've been tearing through this massive stack of highly technical engineering documents, aviation standards, and system architecture blueprints.
Some really dense material.
Oh, incredibly dense. We are talking about the absolute bleeding edge of unmanned aerial vehicle or UAV design.
Right.
The mission of this deep dive is to extract the invisible, hyper-strict rules that keep these autonomous machines in the air. Okay, let's unpack this, because aviation safety, especially in the autonomous realm, isn't about crossing your fingers and hoping your code compiles correctly.
Well, definitely not. You can't just push an update and hope for the best.
No, it is about physically, mathematically, and logically proving that these systems cannot fail in an unpredictable way.
What's fascinating here is that in the aviation world, safety is what we call an emergent property.
An emergent property. What does that actually mean in practice?
Well, you can't just go to an aerospace supplier, buy a black box labeled safety, and bolt it onto your airframe.
Right, like an add-on feature.
Exactly. Safety emerges as a holistic result of obsessed-over design. It's the culmination of thousands of tiny, perfectly executed decisions.
Decisions spanning across everything, right? Like metallurgy, thermodynamics.
Silicon architecture, software logic, all of it. When you orchestrate all those flawless components together, the property of safety emerges from the whole.
I love that concept. It's like a symphony. No single instrument is the music, but together, if they all play perfectly in time, the music happens.
That's a great way to look at it.
And for you listening, the learner who wants the real mechanics behind the curtain, we are giving you the ultimate shortcut today.
We're doing the heavy lifting for you.
We really are. We are bypassing the thousands of pages of incredibly dense DO-178C and DO-254 aviation manuals, and we are extracting the pure engineering reality.
Because honestly, nobody wants to hear us read a manual for an hour.
No one. We're going to treat you like the experts you are. We aren't going to spend 20 minutes explaining basic programming logic. We are going straight into the deep end.
It's a progression that fundamentally alters how you view autonomous systems.
Yeah.
And, to truly understand the brain of the machine, we have to start with the physical vessel.
Right, the body itself.
Yeah, we need to look at the rigid 5-layer architecture, what systems engineers categorize as layer 0 through layer 4.
Let's start at the absolute foundation then. Layer 0, the platform and the power.
The physical stuff.
Exactly. I was looking at the physical specs in the architecture documents, and they detailed these military-grade modular carbon fiber airframes.
Which are incredibly tough.
Oh, they carry an IP45 protection rating, which makes sense.
Yeah.
I mean, you need to survive low-pressure water jets, rain, and snow from basically any direction.
Right. The environment is actively trying to destroy it.
But what really caught my eye was the wind tolerance. These frames are rated to withstand Category 5 winds.
Yeah, that's roughly 10.7 meters per second.
That is a relentless, buffeting shear force, just a constant hammering.
The aerodynamic stress at 10.7 meters per second is immense. And it's not just about the drone getting blown off course.
What else does it do?
It's about the structural integrity of the carbon fiber itself. If you use a cheaper polymer or a poorly laid up carbon composite, the frame actually flexes under that wind shear.
Oh, I see. And if the frame flexes, the geometry of the motors changes relative to the center of gravity, right?
Precisely the issue. If the motor mounts twist even a few degrees out of alignment because the arm is bending,
The thrust vectors are suddenly pointing in the wrong direction?
exactly. The flight algorithms in the higher layers are doing math based on a rigid frame.
Mm-hmm.
If the frame isn't rigid, the IMU, the inertial measurement unit, starts feeding garbage data to the flight controller.
And the drone starts fighting itself.
Yeah, it enters an unrecoverable oscillation. It just shakes itself out of the sky. So layer 0 requires absolute physical rigidity just to validate the math happening in the upper layers.
Wow, so the skeleton has to be unyielding.
Unyielding is a good word for it.
But a tough skeleton is useless without a massive energy source. And the battery specifications in these documents stopped me in my tracks.
The Molicel ones.
Yes, they highlight the Molicel INR 2017-100 series batteries, specifically the P60C and P50B cylindrical cells.
Those are absolute monsters.
The numbers here are just wild. They output 20 amps of continuous discharge and a staggering 100 amps of pulse discharge.
Which is just an unbelievable amount of power.
Right. Now, I understand high-drain batteries, but 100 amps from a single cell string, that is a localized thermal event waiting to happen.
It sounds like a bomb.
Exactly. How is that not a massive fire hazard during rapid maneuvering?
Well, it is an absurd amount of current, and poorly managed, it absolutely leads to thermal runaway. Fire, explosions, all the bad stuff.
So how do they control it?
That 100-amp pulse capability is non-negotiable for explosive maneuvering. I mean, if that 10.7 meter per second wind suddenly shifts into a massive downdraft.
It needs to fight back instantly.
Right, the drone needs instantaneous torque across all 4 or 6 or 8 motors just to punch through it.
Okay, so the power is required.
Yeah. The way they prevent the battery from becoming an incendiary device comes down to the battery management system, or BMS. It has to conform to UL 3030 and UN 38.3 standards.
I was reading about those BMS standards. They don't use mechanical relays to isolate faults, do they? I'd imagine mechanical relays are way too slow.
Oh, way too slow. They rely on solid-state MOSFETs.
Okay, solid state.
Yeah, the BMS is pulling the voltage, current, and temperature of every single cell group thousands of times a second.
Wow.
If it detects a dead short or even a tiny voltage sag that indicates a cell is about to go critical,
And it cuts the power.
it physically isolates that fault in under 5 milliseconds. It breaks the circuit faster than a human can blink.
That is incredibly fast. But there was another thing about those Molicel P50B cells. The real magic isn't just the discharge rate, right? It's the internal DC resistance.
Which plays directly into our negative 40-degree blizzard scenario.
Right, because cold destroys batteries.
Exactly. Internal resistance is basically the enemy of batteries. High resistance means energy is wasted as heat.
Okay.
But more critically, when the ambient temperature drops to negative 40, the chemical kinetics inside a standard lithium-ion cell slow to a crawl.
The chemistry just stops working.
Pretty much. The internal resistance spikes, the voltage plummets under load, and the drone falls out of the sky because the motors can't draw enough power.
So how do the P50B cells survive that?
They have an aggressively low internal resistance, meaning the chemical pathways remain relatively clear even when freezing.
Oh, wow.
Yeah, it maintains a stable voltage under heavy load, even in extreme cold.
Okay, so that covers the pure electric setups. But the architecture docs also dive into hybrid configurations for long-endurance missions.
The fuel cell hybrids, yeah.
Right. Combining PEMFC's proton exchange membrane fuel cells with a lithium battery buffer.
A really interesting approach.
I find fuel cells fascinating because hydrogen has incredible specific energy, roughly 5 times that of lithium batteries by weight.
It's fantastic for range.
But I imagine hydrogen fuel cells aren't exactly known for their rapid dynamic response, are they?
No, they are notoriously sluggish.
Okay, so how does that work in a drone that needs quick reflexes?
Well, the electrochemistry of a PEMFC, basically reacting hydrogen with oxygen across a membrane to generate electricity, is a steady-state process.
It likes to run at a constant speed.
Exactly. If the drone suddenly demands that 100-amp pulse to dodge an obstacle, the fuel cell simply cannot ramp up its chemical reaction fast enough.
The voltage would just collapse.
Right.
So they use a power split strategy, a PSS. I saw that in the docs.
Yep. The architecture uses a highly active DC-DC converter to mediate between the two power sources.
How does it mediate?
The fuel cell acts as the baseline generator, providing the steady cruising power. But the DC-DC converter monitors the transient load.
The sudden spikes.
Exactly. The microsecond the flight controller demands a massive spike in torque, the converter seamlessly shifts the load onto the lithium battery pack.
Ah, and the lithium dumps that 100-amp pulse.
You got it. And once the maneuver is over and the load drops, The DC-DC converter uses the excess baseline power from the fuel cell to slowly recharge the lithium buffer.
That is so smart. It's a brilliant way to mask the dynamic weaknesses of fuel cells using the explosive output of lithium.
It really is the best of both worlds.
Okay, so that's electric and hybrid, but we also have to talk about the internal combustion setups for the heavy lift variants.
The big gas-powered ones.
Yeah, these rely on an engine control unit, the ECU, specifically utilizing a full authority digital engine control, or ADD.
ADD is it's technology pulled straight down from commercial airliners. Yeah. The ECU is micromanaging fuel injection pulse widths and ignition timing. But the true engineering brilliance in this layer isn't in how it operates under normal conditions.
It's how it fails.
Exactly. It's how it fails.
Yes, the power derating algorithm. This absolutely blew my mind when I read it.
It's so counterintuitive.
Okay, think about a standard automotive ECU. If your car engine's cylinder head temperature spikes into the red, the car's computer will aggressively cut fuel or entirely shut the engine down to prevent it from melting the block.
It protects the engine at the cost of mobility.
Right, which is perfectly acceptable when you can coast to the side of a highway.
But you cannot coast a UAV. A shutdown is a catastrophic loss of the airframe.
Right. So the UAV's FADC takes a completely different approach. If it detects the cylinder head temperature or exhaust gas temperature spiking to critical levels, it actively refuses to shut down.
It just keeps going.
Instead, it restricts the maximum throttle to reduce the workload, but then, and this is the crazy part, it deliberately forces a highly rich air-fuel ratio.
It just floods it.
It literally dumps raw, unburned liquid fuel directly into the overheating cylinder.
And from a purely mechanical standpoint, running an engine that rich is terrible for it.
Oh, yeah. You foul the spark plugs, you wash the oil off the cylinder walls.
You destroy fuel efficiency completely.
But the ECU is utilizing the latent heat of vaporization.
Yes, it's basically the engine sweating.
I love the physics of this. When that excess liquid fuel enters the hot cylinder, it evaporates. And phase changes require energy.
A lot of energy.
So the evaporating fuel absorbs massive amounts of heat from the surrounding metal of the cylinder head, cooling the engine from the inside out.
The algorithm basically calculates that it is mathematically preferable to destroy the long-term lifespan of the engine.
Just to survive the next 5 minutes.
Exactly. To buy exactly enough time to execute a safe return protocol. It cools itself with fuel, sends a telemetry warning back to the ground control station, and limps home.
It's a sacrificial safety mechanism. The engine dies so the drone can live.
It's brilliant.
Okay, so layer 0 sorted. We have our rigid carbon skeleton, our blast furnace batteries, and our sacrificial engines. We have the physical brute force.
Now we move up the stack.
Right. Up to layer 1, the flight control platform. If layer 0 is the muscle, layer 1 is the brainstem. It handles the instantaneous reflexes.
Yeah, layer 1 runs on flight stacks like PX4 or Autopilot, running on top of a real-time operating system or RTOS.
And the documents heavily feature NUTX for this, right?
They do. This layer's sole responsibility is taking raw analog data from the IMU, the LiDAR altimeters, and the optical flow sensors.
And making sense of it instantly.
Exactly. It calculates the required thrust vectors and sends PWM signals to the electronic speed controllers to keep the aircraft level.
The documentation stresses the absolute necessity for hard real-time execution here. And for the developers listening, we need to draw a hard line between the OS running on your laptop and a hard RTOS like NUTX.
Oh, it's a massive difference.
Yeah.
The distinction is life or death for the drone.
Oh, so?
Well, general-purpose operating systems like Linux or Windows operate on soft real-time or best effort scheduling.
Meaning they try their best, but they get distracted.
Right. If a process demands CPU time, the OS scheduler might pause it for a few milliseconds to handle a network interrupt or run garbage collection.
And as a user, you don't notice a 10-millisecond stutter when scrolling a web page.
Not at all. But in layer 1, a 10-millisecond stutter means the PID loop, calculating the roll axis, misses a deadline.
And what happens if it misses a deadline?
In a hard real-time system, a missed deadline is considered a total system failure.
Wow, total failure.
Yeah. It is not just delayed data, it is wrong data. The control loops in layer 1 must execute with microsecond determinism.
So it has to happen exactly when it says it will.
Exactly. If a gust of wind hits the drone, the IMU detects the angular acceleration. The NUTX scheduler guarantees CPU time to the flight stack without any preemptive interruptions.
It drops everything else it's doing.
And the PID controller calculates the counter thrust and the signal hits the motors. If this entire pipeline doesn't happen within the strictly defined time window, the physical dynamics of the drone outpace the software.
And it flips over.
It just falls out of the sky.
So the brainstem has to be flawless. It is a constant, relentless balancing act at a microsecond scale.
It is.
But reflexes alone do not make a drone autonomous. I mean, a machine that only knows how to balance is just a very expensive hovering rock.
That's true.
It needs eyes, it needs strategic thinking, and it needs a voice to communicate in a hostile environment.
And this brings us out of the subconscious layer 1 and into the conscious strategic layers of the architecture, layers 2, 3, and 4.
This is the threshold of true robotics. Layer 2 is edge computing and perception.
This is where we alleviate the cognitive load from the human operator and shift the burden of spatial awareness onto the machine itself.
The specs show this layer is driven by NVIDIA Jetson Orin modules running YOLOV 11 machine vision models.
Heavy-duty AI hardware.
Seriously, we are talking about massive parallel processing capabilities, hundreds of TOPS Terra operations per second happening locally on the drone.
That's the key. Locally.
Right. It's not streaming video to a server farm to be analyzed. It's doing it in the air.
The primary function here is high-throughput sensor fusion. A modern drone is equipped with 4K optical cameras, FLIR thermal imaging, and high-density LiDAR.
Which is a ton of data.
It generates gigabytes of raw, unstructured data every single second.
And here is where the bandwidth bottleneck usually kills autonomous operations. I mean, if you try to beam gigabytes of raw 4K video and LiDAR point clouds back to a ground control station over a radio link,
you will instantly choke your bandwidth.
Especially in a military or emergency response scenario where the electromagnetic spectrum is crowded or actively jammed.
Which is exactly why Layer 2 performs semantic compression.
Semantic compression. Break that down for me.
Well, it doesn't compress the video like an H.265 codec, just making the file smaller. It fundamentally translates the video into meaning. The YOLOV model processes the raw visual feed, identifies objects, calculates their bounding boxes, and derives their velocity.
So instead of transmitting millions of pixels back to base,
the Jetson Orin distills that data into a lightweight JSON string or a binary structured format.
So it's essentially turning a massive video feed into a tiny text message. It says, threat object identified, vehicle, coordinates XY, heading 045, speed 60 kilometers.
Exactly. It extracts the threat features from the noise.
That saves so much bandwidth.
And this allows for vision-based navigation in totally GPS-denied environments too.
How does that work?
If the GPS is spoofed, the drone compares its live semantic understanding of the terrain against preloaded topographical maps. It matches visual landmarks to stay on course.
All without needing to ask the ground station for help.
Exactly.
So the drone understands its environment and knows where it is and what's around it. Now it needs to make strategic decisions based on that data, which is Layer 3, the mission system and command and control, or C2.
The strategic brain.
Right. And here's where it gets really interesting. The architecture incorporates large language models, LLMs, directly into the ground control station integration.
The integration of LLMs at the C2 layer is a total paradigm shift in human-machine teaming.
It's wild to think about ChatGPT flying a drone.
Well, historically, operating a complex UAV required a highly trained pilot staring at incredibly dense telemetry dashboards.
Just screens full of numbers.
Right. Monitoring voltage sags, pitch roll indicators, thermal readouts, and trying to mentally synthesize all that into situational awareness.
It's an immense cognitive load for a human. But by bridging the GCS with an LLM, you change the interface from raw data to natural language intent.
Exactly. The operator no longer has to manually program a complex multi-waypoint patrol route while adjusting camera gimbal angles.
They can just talk to it.
Yeah, they can simply input a natural language command. Establish a 1-kilometer perimeter scan around this facility, prioritize thermal anomalies, and maintain radio silence unless a target is identified.
And the drone just understands that.
The LLM parses that intent, translates it into the rigid deterministic waypoint and payload commands required by Layer 2 and Layer 1, and then it monitors the incoming telemetry, reporting back in plain English.
That is incredible. The sources also detail the use of VR telemetry at this layer.
Yeah, the VR stuff is really cool.
The operator can put on a virtual reality headset and get a fully immersive 3D threat analysis, because Layer 2 is sending back structured data and LiDAR meshes instead of flat video.
The GCS can render a 3D environment in real time.
You are effectively projecting the operator's consciousness into the drone's spatial map.
It drastically reduces the OD loop, the observe, orient, decide, act cycle.
Right. But all of this processing, the AI, the natural language parsing, it relies on one critical assumption, that the drone can actually communicate with the ground station.
And if the link is severed, the strategic layers are completely isolated.
And that is the domain of Layer 4, mission communications and collaboration.
The drone's voice and ears.
Exactly. I was looking at the communication hardware, and they rely heavily on SDR software-defined radio for dynamic spectrum switching.
It's essential for surviving in modern airspace.
But I have to push back here on the realities of modern electronic warfare. Armies and even sophisticated non-state actors use massive multi-kilowatt jammers to blast the electromagnetic spectrum with broadband white noise.
It's a huge problem, yeah.
They raise the noise floor so high that radio signals are completely drowned out. If Layer 2 is relying on Layer 4 to send back those semantic JSON strings, how does the SDR survive an intense jamming environment? I mean, how does any signal punch through that wall of static?
This resilience comes from the synergy between Layer 2's data compression and Layer 4's antenna array.
How do they work together?
Because Layer 2 has already compressed the gigabytes of video into a microscopic sliver of data, Layer 4 doesn't need a wideband connection.
Oh, it just needs a tiny crack to slip through.
Exactly. It only needs a tiny fraction of the spectrum to slip a message through. To defend that tiny signal, Layer 4 utilizes CRPA technology-controlled reception pattern antennas.
CRPA. The documents mention this uses null steering and zero-point generation. The physics of this are fascinating. Walk us through how a CRPA physically ignores a jammer.
So a traditional omnidirectional antenna listens to the entire environment equally. If a powerful jammer is blasting from the east, the antenna is deafened, the receiver's front end is saturated.
It just hears white noise.
Right. But a CRPA, however, is not a single antenna. It is an array of multiple, highly synchronized antenna elements spaced precisely apart on the drone's chassis.
So it's listening from multiple physical locations simultaneously.
Yes. And because of that spacing, when the jamming signal hits the drone, the RF waves hit each individual antenna element at a microscopically different time.
Because of the speed of light.
Exactly. We're talking picoseconds of difference depending on the angle of arrival.
Yeah.
FPGA behind the CRPA array calculates this time difference of arrival.
Okay, so it uses that time difference to do what?
It uses that math to pinpoint the exact three-dimensional vector of the jamming source. It knows exactly where the noise is coming from.
And once it knows exactly where the noise is coming from, how does it block it?
It uses destructive wave interference. The software dynamically shifts the phase of the signals coming from the different antenna elements and adds them together.
Wait, so it inverts the waves?
Yes. By perfectly inverting the phase of the incoming jamming signal, the waves cancel each other out mathematically.
That is wild.
The system generates a localized null, basically a blind spot or a cone of silence in its own reception pattern, and steers that blind spot to point directly at the jammer.
It essentially puts a mathematical finger in its ear, but only in the exact direction of the hostile noise.
Exactly. The jammer is effectively muted in the RF front end, allowing the CRPA to continue listening for the faint, highly compressed data packets coming from the friendly ground station in other directions.
It is dynamic, real-time spatial filtering.
Yeah.
That is just an incredible piece of engineering.
It really is.
So we have this brilliant architecture. Layer 0 provides the muscle. Layer 1 handles the microsecond reflexes. Layer 2 processes the visual world. Layer 3 plans the mission. And Layer 4 surgically slices through electronic warfare.
It's quite a stack.
But listening to all of this, I can't help but think about the foundational fragility of the silicon running it all.
The hardware layer.
Yeah, we have all these brilliant algorithms, but they rely on FPGAs, ASICs, and microprocessors containing billions of microscopic logic gates. What if the chip itself has a fundamental flaw? What if the silicon brain is wired wrong from the factory?
That is the nightmare scenario that keeps aerospace engineers awake at night. If the fundamental hardware logic is flawed, no amount of brilliant software can save the system.
Right.
And that fear is the exact reason we have DO-254 hardware certification.
DO-254, the standard for exercising the ghost in the machine. We are pivoting now from what the drone can do to how we mathematically prove it is safe to do it.
This is where things get really strict.
The sources define DO-254 as the global aviation standard for complex electronic hardware. We are talking about FPGAs, field-programmable gate arrays, and ASICs application-specific integrated circuits.
Right, and FPGAs are heavily used in layers 1, 2, and 4 because they offer hardware-level parallel processing.
Which is much faster than running things in software.
Exactly. An FPGA is essentially a blank canvas of millions of logic gates that hardware engineers program using an HDL, a hardware description language like VHDL or Verilog, to wire up custom circuits on the fly.
And the documentation makes a massive bright line distinction here that we really have to clarify. DO-254 is absolutely not about random hardware wear and tear.
No, it's not.
It's not checking if a capacitor degraded over 10 years or if a resistor popped due to heat. DO-254 is designed entirely to prevent design errors.
The distinction between a random fault and a design error is critical in aviation. Random hardware failures are dictated by physics and thermodynamics. Things eventually wear out.
You can't beat entropy.
Exactly. And you mitigate random failures with redundancy. You put 3 independent altimeters on the drone instead of 1. If one pops a capacitor, the other 2 vote it out.
But a design error bypasses redundancy entirely.
Completely. A design error is a fundamental flaw in the logic. It is the fatal gap between what the systems engineer intended the chip to do and how the hardware engineer actually coded the millions of logic gates to behave.
So if the logic is bad...
If there is a logical flaw in how an FPGA handles a specific edge case interrupt, and you put 3 redundant FPGAs on the drone, redundancy won't save you.
Because they all have the exact same flaw.
Right. All 3 chips will execute the exact same flawed logic at the exact same microsecond, and the drone will suffer a total simultaneous loss of control.
Okay, so if building complex hardware is like building a massive city grid, DO-254 isn't checking if a single traffic light bulb burned out.
No.
It is mathematically proving that it is impossible for all the traffic lights at a major intersection to turn green at the exact same time, no matter what inputs are fed into the system.
That's a perfect analogy.
Yeah.
And if we connect this to the bigger picture, the mechanism DO-254 uses to prove that impossibility is the traceability matrix.
The traceability matrix.
And this is where the sheer rigor of aerospace engineering separates itself from commercial electronics.
It sounds like an auditor's absolute dream and a hardware engineer's worst nightmare.
It is exhausting, but totally necessary. DO-254 maps hardware criticality based on DLL's design assurance levels.
Ranging from A to E, right?
Yeah. DLA is catastrophic, meaning a failure leads to the loss of the aircraft or human life. DLE is no effect. For DLA and B hardware, the traceability matrix requires exhaustive, unbroken lifecycle traceability.
Break down what unbroken traceability actually means for the engineers writing the HDL code.
It means every single logic gate, every single line of Verilog must trace all the way back up to a specific written high-level system requirement.
So an example would be...
The systems engineer writes a requirement. The system must deploy the parachute if pitch exceeds 90 degrees. The hardware engineer writes the logic to execute that. The traceability matrix physically links that line of code to that requirement document.
So what happens if a brilliant hardware engineer throws in a clever little optimization? Say they realize they can save a few clock cycles by adding a bypass logic gate, making the chip run 5% faster. But that specific bypass gate isn't explicitly linked to a high-level system requirement.
The certification fails immediately.
Wow, just like that.
In DO-254, if a logic gate exists on the silicon that does not explicitly map back to a requirement, it is categorized as an unverified, unpredictable variable.
Even if it makes the chip better.
It does not matter how clever the optimization is or how much faster it makes the chip. In aviation, unverified cleverness is viewed as a fatal, unacceptable risk. You have to go back, write a requirement for the optimization, and then verify it.
And the verification process itself is grueling. The sources detail the use of static analysis and dynamic simulation. Engineers have to prove the HDL logic works perfectly under every conceivable permutation of clock cycles and inputs.
It takes months.
But what really fascinated me is that DO-254 forces engineers to account for the actual cosmos interfering with the silicon.
Ah, yes. Single event upsets, or SEUs. This is where physics literally attacks logic.
It sounds like pure science fiction. Walk us through the mechanics of an SEU.
As a UAV ascends to higher altitudes, the Earth's atmosphere thins out, providing less shielding against cosmic radiation.
Okay, so more radiation.
High-energy particles, neutrons, and protons from space are constantly bombarding the aircraft. Occasionally, one of these high-energy particles will pass directly through the silicon lattice of an FPGA.
Like a microscopic bullet.
Exactly.
Yeah.
And if it strikes a transistor holding a charge in a memory register with just enough kinetic energy, it can literally flip the state of that transistor.
You mean it changes the data?
It changes a logical 0 to a 1, or a 1 to a 0. That bit flip is a single event upset.
So the cosmos literally reaches down and corrupts the data. If that bit flip happens in the register holding the drone's altitude variable, the drone suddenly thinks it's at 0 feet when it's really at 10,000, and it cuts the engines.
Which is exactly why DO-254 mandates that for DLA hardware, the logic must be designed to survive SEUs without resulting in an unpredicted state transition.
You have to build immunity into the chip.
You have to implement mitigation strategies directly into the hardware fabric.
Like triple modular redundancy.
TMR is the standard approach, yeah. At the logic gate level, you don't just calculate a variable once, you instantiate 3 separate logic circuits on the FPGA to calculate the exact same variable in parallel, and then feed their outputs into a voting circuit.
Okay, so a vote happens every time.
Yeah. If a cosmic ray flips a bit in circuit A, circuit B and C will still output the correct value. The voting circuit sees that B and C agree, realizes A is corrupted, ignores A, and passes the correct value forward.
And all that happens within a single clock cycle.
All within a single clock cycle.
The amount of logic overhead and engineering hours required to implement TMR across a complex chip is just staggering. It explains why the documentation notes a massive shift in the industry towards COTS hardware commercial off-the-shelf components.
Oh, absolutely. Developing a bespoke DO-254 DAL, a certified ASIC or FPGA from scratch, can cost tens of millions of dollars and take years of documentation.
Just to prove the logic.
Exactly. So to accelerate development, manufacturers are now buying pre-certified COTS microprocessors. The vendor has already spent the millions to prove the traceability matrix and the SEU mitigation, and they sell the chip along with a massive binder of certification artifacts.
The drone manufacturer just buys the binder and integrates it.
Pretty much.
Okay, so DO-254 secures the physical silicon grid. The hardware brain is logically flawless, immune to design errors and cosmic rays. But if the physical brain is perfect, it's completely useless if the thoughts running through it are schizophrenic.
Right, the software.
You can have a perfect FPGA, but a single infinite while loop or a single buffer overflow in the software will bring the whole multi-million-dollar airframe crashing down. That brings us to Section 4, the Unbreakable Code, governed by DO-178C.
DO-178C is the absolute golden standard for aviation software. It is arguably the most rigorous software development standard on the planet. Period. And its core philosophy is a mantra that every single software developer should have tattooed on their arm. Safety is not tested into a system, it is designed into it.
Safety is designed, not tested. That is a profound cultural shift from how 99% of commercial software is built today.
Oh, yeah.
You don't build a messy, sprawling application and then rely on a QA team to hunt down the bugs during testing. You architect it flawlessly from line one. And just like the hardware standard, DO-178C demands intense traceability.
Yeah, bidirectional traceability.
Yeah.
The documentation flow is a rigid waterfall.
How does it flow?
System requirements dictate the high-level software requirements. Those dictate the low-level design architecture. The design dictates the actual source code. And the source code dictates the test cases.
But it has to flow upwards too, doesn't it?
Exactly. Every single executed test case must map back to a specific line of code, which maps back up to the design, back up to the requirements.
Everything has to have a purpose.
If you have code that doesn't map to a requirement, or a requirement that doesn't have a test case, the entire chain is broken.
And this bidirectional chain leads to the absolute unforgiving ban on dead code and deactivated code.
This is a massive stumbling block for developers transitioning from web or app development into aerospace.
Because in normal software, if you deprecate a feature or if you write a debugging script, you often just comment it out or leave the unused functions in the code base.
Right, it doesn't hurt anything, usually.
But in DO-178C, living dead code in the compiled binary is a critical failure. Why is it so strict?
Because if compiled code exists on the flight controller, and it is never called during normal operations, it means it is untested.
And untested means unknown.
Exactly. If it's untested, you have no mathematical proof of what it will do if a random memory pointer accidentally executes it. An unexpected error could trigger a legacy debugging function, and suddenly the drone is dumping its RAM to a serial port instead of calculating rotor RPMs.
You cannot have unknowns. It demands 100% determinism. Now let's get into the weeds on how they actually test the code that is supposed to be there. The structural coverage analysis.
The testing phase.
For DLA and DLB software, the testing is brutal. But DLA introduces a specific metric that is notorious in the software engineering world. MCDC, Modified Condition Decision Coverage.
Achieving 100% MCDC is the technical crucible that breaks many development teams.
To understand the gravity of MCDC, you have to look at how complex Boolean logic statements are evaluated in software.
Yeah. Let's set up a scenario. We don't need to explain basic Boolean logic. We know our ANDs and ORs. But let's contextualize it for the flight controller.
Right. Let's say you have a critical function for deploying an emergency recovery parachute.
Okay, good example. The code contains an IF statement with multiple conditions. If altitude is below 100 meters AND, descent rate is greater than 10 meters per second AND, all motors are ezelit, offline or manual override is true, then deploy the chute.
That's a pretty standard block of logic. In standard commercial software testing, a developer might just write branch coverage tests.
Right, checking if it goes left or right.
They write one test where the whole statement evaluates to true, ensuring the parachute deploys, and one test where it evaluates to false, ensuring it doesn't.
But branch coverage is woefully inadequate for aviation. It doesn't prove that every individual variable in that complex statement actually functions correctly.
So what does MCDC require?
MCDC requires you to prove that every single condition within a decision can independently affect the outcome of that decision, while all other conditions are held constant.
So you have to isolate the variables?
You have to create a massive matrix of test vectors. You must prove that toggling only the altitude condition from true to false flips the final outcome. Then you hold altitude constant and prove that toggling only the descent rate condition flips the outcome.
You have to do this for every single Boolean operand in the entire flight control stack.
For every single one. The combinatorial explosion of test cases required for a code base with millions of lines of code is staggering.
Which is why achieving 100% MCDC is almost impossible without massive automated tooling and static analysis frameworks.
It actually forces developers to write simpler, less nested code. If you write a deeply nested, highly complex Boolean statement, you will spend weeks just writing the MCDC test vectors for that one single function.
And the constraints on how they actually write the C or C++ code are just as draconian. The sources mention the strict adoption of coding standards like MIS-RAC 2012.
MIS-RAC is a subset of the C programming language specifically designed for safety-critical systems.
Because standard C can be pretty wild.
C is a very powerful language, but it allows developers to do very dangerous things with memory if they aren't careful. MIS-RAC eliminates those dangers by outlawing certain language features entirely.
For instance, it places an absolute ban on dynamic memory allocation. You cannot use the malloc or free commands anywhere in a flight controller.
Which sounds completely insane to a modern software engineer. Dynamic memory allocation is foundational to most software.
Right. When you use malloc, you are asking the operating system to dynamically carve out some free RAM on the heap while the program is actively running.
But the danger there is memory fragmentation and memory leaks.
If a function allocates memory dynamically, uses it, and fails to free it properly, a memory leak, the system slowly consumes all available RAM.
Until the stack collides with the heap and the flight controller suffers a hard crash, in aviation, you cannot rely on dynamic allocation.
So how do they get memory? By banning malloc, all memory must be allocated statically at compile time. The exact memory footprint of the entire software suite is calculated and locked in before the drone ever leaves the ground. That mathematically eliminates the possibility of an out-of-memory error during flight.
Exactly. MIS-RAC also bans recursive functions, by the way. You cannot have a function call itself.
Because recursion can lead to an infinite loop.
Which leads to a stack overflow.
Right.
Everything is about eliminating undefined compiler behaviors and ensuring absolute determinism.
I have to push back here on behalf of modern development philosophies. In the tech world, Silicon Valley, SaaS, app development, we constantly hear about agile methodologies.
Move fast and break things.
Yes, moving fast, breaking things, pushing daily CI/CD pipelines, containerized microservices, A/B testing on live users. Why can't aerospace adopt this? Why can't we sandbox the flight controller, containerize the YOLO-11 AI, and just push over-the-air updates using agile sprints to fix bugs as we find them?
It's a debate happening right now in the industry, and it highlights a massive cultural divide. The fatal flaw of move fast and break things in aerospace is the physical consequence of the breakage.
It's not just a digital error.
Right. When a cloud-based microservice breaks, a user gets a 404 error, you roll back the container and nobody is hurt. When a 200-kilogram autonomous UAV flying over an urban center experiences a software fault, it becomes a kinetic weapon.
As you said earlier, you can't A/B test gravity.
You cannot. Now, to your point about containerization, yes, we are seeing partitioning. DO-178C allows for mixed criticality systems using ARANC 653 standards.
So you can split things up.
You can partition the payload, say the camera UI or the LLM parsing in Layer 3, into a separate memory space from the Layer 1 flight controller.
Okay.
You might push faster updates to the camera UI. But the core flight stack cannot be agile.
Oh my God.
DO-178C demands independence.
Hmm.
For DALA and B software, the engineer who tests the code cannot be the engineer who wrote it.
You cannot grade your own homework.
And the sheer volume of static analysis required using tools like polyspace and LDRA means that every single line of code is mathematically checked for race conditions, divide by zero errors, and timing violations before it is ever compiled.
So it's incredibly slow.
You cannot iterate rapidly in a daily sprint, when every minor iteration requires weeks of regression testing and re-verification of the NCDC coverage. Deterministic execution is the goal, not speed to market.
Wow. Okay, so let's zoom out and look at what we've built. We have the L0 to L4 physical architecture holding it all together. We have DO-254 ensuring our hardware logic is mathematically perfect and immune to cosmic rays.
And DO-178C for the code.
Right, ensuring our software is statically allocated and structurally flawless. But disaster rarely strikes in the middle of a perfect silo. It strikes at the intersections.
That's where things always go wrong.
What happens when the perfect software meets the perfect hardware, but they misunderstand each other? Or what happens when the physical world actively tries to destroy the airframe? This brings us to Section 5, Holistic System Health, covering ARP 4754A, ISO 26262, and the brutal environmental realities of DO-160G.
The intersections are indeed the most dangerous domains. You can have a flawlessly coded software driver written in MIS-RC and a perfectly designed hardware sensor certified to DO-254.
Both are perfect in a vacuum.
Exactly. But if the software team expects the sensor data to arrive in milliseconds and the hardware team designed the sensor to output in microseconds, the system will crash the moment they are integrated.
The sources refer to this as semantic ambiguity.
It's the breakdown of the interface control document. To bridge this gap, the aerospace industry relies on SAE ARP 4754A.
Is that another coding standard?
No, this is not a coding standard. It is a systems engineering guideline that governs the entire development lifecycle. Its primary objective is to force cross-disciplinary integration.
It forces the software engineers and the hardware engineers into the same room.
It forces them to agree, unequivocally, on the system requirements early on, eliminating semantic ambiguity at the boundaries between disciplines. It ensures that the assumptions made by the software team perfectly align with the physical realities of the hardware team.
The sources also bring up ISO 26262 in this context. Now, I know ISO 26262 is originally an automotive standard for functional safety. Why is an automotive standard being adapted into UAV architecture alongside aviation standards?
Because they address different failure domains. DO-254 handles design errors, the logical mistakes made by engineers during development.
Right.
But DO-254 does not address the physical degradation of the hardware over time. ISO 26262 is fantastic at handling random hardware faults.
The wear and tear, the bathtub curve of reliability.
Exactly. A sensor degrading due to thermal cycling over 1,000 flights. A wire vibrating loose due to aerodynamic flutter.
How does it measure that?
ISO 26262 uses metrics like FET, rates failures. In time to calculate the probability of these random faults occurring. It dictates how the system architecture should detect those random faults and fail gracefully.
Graceful failure.
It works in tandem with the Functional Hazard Assessment, or FHA, which is conducted very early in the ARP 4754A design phase to allocate those DAL levels based on the severity of potential hazards.
But no amount of elegant systems engineering or graceful failure logic can save a UAV if its internal wiring melts or if it gets blasted out of the sky by a thunderstorm.
That's where it gets physical.
And that is where the D160G standard comes in. This is the environmental testing standard. And reading these protocols, it reads less like engineering and more like orchestrated torture.
D160G is where theory meets physical brutality. It's not about checking logic gates. It's about proving physical survival in environmental hell.
Let's talk about some of these tests. Altitude testing, for one. They place the avionics in vacuum chambers simulating 6,500 meters of altitude.
The primary concern at 6,500 liters isn't just the lack of oxygen, it's the lack of convective cooling.
Because the air is too thin to carry the heat away.
Exactly. In a thin atmosphere, the heat generated by that massive NVIDIA Jetson Orin chip in Layer 2 has nowhere to go. D160G verifies that the thermal management system, the heat sinks, the thermal paste, the internal airflow, can prevent the microprocessors from literally desoldering themselves in a near vacuum.
And then there is Section 22 of DO-160G, the lightning strike simulation.
That's a wild test.
We are talking about injecting massive multi-million volt transient energy spikes directly into the internal wiring harnesses of the drone.
Because an aircraft acts as a massive conductor in a thunderstorm. If lightning strikes a carbon fiber wing, the physical damage is one thing, but the electromagnetic pulse travels through the airframe and induces massive voltage spikes in the copper wiring running to the flight controller,
Frying everything inside.
If the UAV's internal electronics aren't shielded properly, if they don't have adequate transient voltage suppression diodes and Faraday cage enclosures, a lightning strike will turn the flight controller into vaporized silicon.
The standard also mandates severe EMI and EMC testing electromagnetic interference and compatibility.
Yeah, they place the entire UAV in an anechoic chamber, a room completely shielded from outside radio waves, lined with those foam spikes to absorb RF energy.
And then what?
Then, they blast the drone with high-power radio frequencies, sometimes sweeping across the spectrum at up to 200 volts per meter.
They are actively tricked to induce an electronic seizure in the drone.
They need to mathematically prove that the drone's brain won't randomly reboot or drop a packet when it flies past a high-power civilian radar station or a massive TV transmission tower in an urban environment.
So we have the software, we have the hardware, we have the physical shock testing, but how do we actually bring all of this together and test the integrated system before we risk a multi-million-dollar prototype in the real sky?
That's where the simulations come in.
The sources detail a fascinating process called HIL hardware-in-the-loop simulations.
HL testing is where the matrix meets reality. It is the final proving ground.
This sounds exactly like the Matrix for drones. From what I understand, they take the actual physical ECU and the flight controller, the real silicon brain that will fly the drone, and they mount it on a test bench.
Right.
But instead of plugging it into real motors and real sensors, they plug its I/O pins into a massive supercomputer running a hyper-realistic physics engine, like Gazebo 3D.
The physical brain is completely tricked into thinking it is actually flying. The supercomputer simulates the exact electrical signals that a real LiDAR sensor would output. It simulates the exact voltage drop of the mollisol battery.
It's indistinguishable from reality for the drone.
Exactly. The brain feels the virtual wind, it calculates the thrust, and it sends PWM signals back to the supercomputer, which instantly updates the drone's position in the virtual world.
And while the physical brain is happily flying in the Matrix, the engineers ruthlessly attack it.
They inject virtual chaos. They simulate a motor suddenly seizing mid-flight. They simulate a total loss of GPS. They simulate the battery temperature spiking to critical levels or a massive downdraft hitting the airframe.
And they watch exactly how the physical hardware and the DO-178C software react to the cascade of failures.
It's all about observing the reaction.
But this brings up a philosophical engineering question. How do you prove the drone can handle aerodynamic chaos that you haven't even thought of yet? I mean, human engineers can only write so many specific failure scenarios.
You automate the chaos. They don't just run 10 or 20 scripted scenarios. They run automated Monte Carlo simulations on the HEL rig.
Monte Carlo simulations, like rolling dice millions of times.
Precisely. The supercomputer randomizes thousands of variables simultaneously: wind speed, air density, sensor noise profiles, motor degradation curves, center of gravity shifts. It runs tens of thousands of flight permutations overnight.
It tests the extreme edge cases of aerodynamic chaos that a human engineer might never think to script.
Exactly. So by the time the actual physical drone is taken out to the runway for its very first real-world test flight,
It has already flown tens of thousands of hours in the Matrix.
it has experienced and survived every possible combinatorial disaster. The goal of HAL testing is that when the drone finally touches the real sky, there are absolutely zero surprises.
Zero surprises. That is the ultimate ethos of everything we've talked about today. We started this journey imagining a rigid carbon fiber drone battling a minus 40-degree blizzard, powered by the sheer chemical brute force of 100-amp pulse batteries.
We covered a lot of ground.
We really did. We built up a 5-layer architecture, moving from microsecond RTOS reflexes to LLM-driven strategic AI and zero-point steering CRPA antennas. And then we locked that brilliant capability down with the ruthless, unforgiving, mathematically proven standards of DO-254 for the hardware, DO-178C for the kind, and DO-160G for the physical environment.
It is a monumental achievement of human engineering and systems architecture to make these highly complex autonomous flying machines so profoundly, boringly reliable.
Boringly reliable. I love that framing. And that leaves us with a final provocative thought for you, the learner, to mull over as we wrap up this deep dive.
What's the thought?
Well, as we look toward the horizon, we are entering the era of software-defined vehicles, urban flying taxis, eVTOLs, and massive autonomous delivery networks that will soon fill our skies and our streets. These extreme aviation standards, the MCDC coverage, the traceability matrices, the ban on dynamic memory, are quietly bleeding downward into our everyday lives.
That's very true.
The electric car sitting in your driveway right now might soon be running autonomous driving code tested to the exact same grueling standards as a military UAV. But if the absolute non-negotiable rule of aviation is that safety is designed, not tested, and that design process takes years of painstaking mathematical proof, how is that going to collide with the breakneck, agile, profit-driven pace of consumer technology? When the move fast and break things culture of Silicon Valley slams into the rigorous ironclad standards of aviation, who is going to adapt to whom?
That is the multi-billion-dollar question that will define the next decade of autonomous transportation.
It certainly is. Thank you for taking this deep dive with us today. We covered a massive amount of technical ground. The next time you see a drone hovering effortlessly in the sky fighting the wind, or the next time you step into a highly automated vehicle, just remember, you are looking at a machine that rests on a massive, invisible foundation of incredible, mathematically proven engineering. You just can't see the X-ray. Keep learning, and we'll see you on the next deep dive.